Hello everyone, my name is Jaisinghani and today I will be presenting the topic Dynamic Response Analysis of a Monopole tower for a customized small rooftop mounted wind turbine. These are the contents of my talk. First we will discuss the introduction of the project, then the loads that the wind turbine tower experiences, followed by the tower geometry and the model used, the analysis methodology, summarizing with the results and the references. India has a lot of wind potential. Actually, 7 windiest states in India can provide for approximately 74% of the installed wind capacity, and this is excluding Ladakh, which can provide for the rest. To train for the wind energy, to see the rising growth in wind energy, and to the need to train wind energy professionals, and to also optimize the production methodology, we are aiming to build a small, scalable, three-bladed horizontal axis wind turbine for initiation of research and development and technical education at IIT Kharagpur. These are the design goals and ceiling features for the wind turbine. So we'll be having focusing on low construction cost, use of simple machinery, simple fabrication process, and having an active control and gathering data from a pilot project. These are the design steps that were used to arrive at this model for the wind turbine, and we will be focusing on the tower design process for our work. So for the tower design, different some of the variables were already predetermined while in the preliminary design process, like the tower height, and some of the variables like the thickness of the tower were then determined in this step. So the thickness of the tower is determined by the buckling load from the nacelle wave, and also we can add buttresses at the base of the tower to provide increase the base fixity of the tower. So we'll be in this work we'll be trying to answer the following questions: what are the natural frequencies of the tower? What is the structural damping? And can the wind turbine tower withstand the following loads: the turbulent load, the gust loads, the vortex-induced vibration loads, the extreme wind loads, and the earthquake loads. So we'll be doing this by first analyzing, evaluating the natural frequencies of the tower, followed by dynamic response analysis of each of the subcases of the loading. So this is the tallest building in our institute campus, on whose rooftop the tower will be mounted. The building height is 30.6 meters. So the 22-month wind data for this particular site was already available to us courtesy to a professor from another department, which shows us that the average wind speed for the site was around 1.82 meter per second. You can see the wind speed probability distribution for the site, and on the right you can see the 360-degree probability distribution, which gives us the dominant wind directions for our particular site. Here we see the basic tower geometry, and our rated power for the turbine is 250 watts, the rotor diameter of 6.8 meters, and the height of the tower for our concept is 4 meters. So out of the total 1500 watts available at the site, the blades can capture 406 watts. This is quite low because the tower is stall regulated instead of pitch regulation, which is available in large commercial wind turbines. These are the major design parameters for the whole wind turbine. These are not necessary for our case, just we will be focusing on the tower. So the turbine experiences large different kinds of loads. So the first is turbulent load. These are random fluctuations of the wind which are present at all the heights above the ground level. And next we have the gust loading, which is a sudden increase in the wind speeds, and it causes a ringing behavior of the tower at its natural frequency. Next we have the vortex-induced vibration. These are caused by the alternate vortex shedding of the vortex shedding caused due to the steady flow of wind across a circular cross section. And these are excited at the vortex shedding frequency. The tower is excited at the vortex shedding frequency. Next, lastly, we have the earthquake loads. From the data we had, we are trying to create the wind energy spectrum to get the analysis for our turbine. So first we take a look at the typical spectrum. So on the left hand side, we have the mesoscale of the spectrum, where the synoptic and diurnal peaks exist. And these peaks normally cause static deflection on the tower. So for the turbulent loading, we are interested in the right hand side of the spectrum, where we'll have the turbulent peak. So next we'll have the plot of the spectrum for our data at site. So on the right we see the wind spectrum, which we plotted from the data that we had available with us. And we can see the synoptic and diurnal peaks, but unfortunately the data cannot model the turbulent part of the spectrum. This is because the interval between the data capture is 30 minutes, and that is too high for our turbulent part of the spectrum, which will be at a higher frequencies. So we will empirically model that part of the spectrum, the turbulent part, using the Kaiman spectrum. And these are the parameters that we use to model the Kaiman spectrum, customizing it to our terrain. And with customization, we got the turbulent intensity of around 21%. And this is the plot for the Kaiman spectrum. You can see the turbulent peak is occurring at around 375 seconds. So the Kaiman spectrum gives us the spectral intensity, but now we want the speed as a function of time to calculate the force variation with the time. So we do an inverse Fourier transform on the spectrum to get the speed variation, which is then used to calculate the force variation with time, which is plotted below. And we can see the force is oscillating around the mean point, and the mean force is caused due to the mean wind speed of the which is the mean wind speed, which is 1.8 volts. The gust loading, to model the gust loading, we are using a deterministic discrete model of gust or rising and falling gust for 5 different gust durations. And to get the velocity function, these are the equations that were used to finally arrive at the force variation with time during the gust durations. Next, we have the vortex-induced vibration. As discussed earlier, vortex-induced vibration occur at the alternate vortex shedding frequency. So to calculate that, we calculate that using the Strohal number, and the Strohal number is calculated experimentally depending on the Reynolds number range. In our case, in our range of Reynolds number, the Strohal number is consistently at 0.2. So we get the alternate vortex shedding frequency at 1.123 Hz. And these are the variables that we use to calculate the vortex shedding frequency. Next, lastly, we have the extreme and seismic loads. The turbine tower is designed for the maximum wind speeds of 50 meters per second. Ironically, at these high wind speeds, the tower just shows a static deflection. But we have ensured that the tower has sufficient restoring block to counter the total overturning we have the sufficient restoring moment to counter the overturning moment that the wind produces. And our tower is located in this region which is also seismic zone 3 according to the National Institute of Seismology, which is considered safe from earthquakes. So we have not considered the seismic analysis of the tower in our study. To model the tower, we have modeled the tower as a uniform, homogeneous, hollow isotropic Euler Bernoulli beam with the nacelle at the top modeled as a tip box. And these are the variables of the tower, which are basically the height is 4 meters and the tower diameter is 324 millimeters. To analyze the dynamic response of the tower, we first calculate the calculate the natural frequencies of the tower. So to calculate the natural frequencies, this is the governing differential equation for free vibration of the tower without any excitation forces. So the first two terms represent the tower and the nacelle inertia, and the third term represents the tower stiffness. The last term represents the nacelle weight. The first two terms here contribute to the kinetic energy of the tower, and the last two terms contribute towards the potential energy of the tower. And the boundary conditions are shown here. At the root, the deflection and slope is 0, and at the tip, the bending moment is 0, and the shear force is balanced by the nacelle inertia. The modeling for the free vibration was done in ANSYS, and we got the natural frequencies and the mode shapes using that. For the dynamic response, this is the governing differential equation. We have the excitation thrust force on the right hand side, which is directly proportional to the density of air, the windage area, the square of the wind speed, and the thrust coefficient, which is considered one for conservative estimates. And the time series analysis was done in StatPro and was also verified using ANSYS. So the different the different loading cases cause a different dynamic response from the tower. So the turbulent loading causes a random inflow response at the excitation frequency, and the gust loading causes a transient response of the tower at the natural frequency, which was also referred as the ringing behavior earlier. The vortex shedding causes a dynamic cross-flow response at the vortex shedding frequency. And finally, the extreme wind causes a quasi-static response, which was also discussed earlier. This brings us to the results. First, we'll see the natural frequencies that were evaluated for the bare tower as well as the tower with the nacelle. We can see the addition of the tower causes a significant reduction in the natural frequencies, as much as 47.4% for the first frequency. This is because of two reasons. The kinetic energy of the nacelle adds kinetic energy, but does not increase the potential energy of the tower. And also the compressive loads due to the nacelle causes a decrease in overall potential energy. Here we can see the mode shapes for the bare tower and with the nacelle. We can see at the tip the nacelle inertia causes a containment of the deflections. There is a slight difference between the two, but you can definitely see that the deflections are contained in the second one and in the tip of the second mode shapes. So this brings us to the dynamic response results. First, we have the turbulent results. We had calculated the turbulent peak at 375 seconds, which gave us a frequency of 0.0026 Hz. And we got the tuning factor quite low as 0.00026, which will not cause any resonance of the structure at our wind speeds. And there will be some fatigue loading, but it is well within the endurance limit of the material. And we can see that the damping causes a significant reduction in the amplitudes, which is already in the order of microns. So we can say that the structure is safe from turbulent loading. Next, the gust wind response. Here we see that there is a short duration transient load, so it will cause a ringing effect on the structure, and the maximum deflection at our wind speeds is even in the order of microns. But we see that the damping causes a significant reduction, a quite early reduction in the oscillations of the structure. And here there will be no fatigue loading as it's a short duration response. Next, coming to the second last subcase of vortex induced vibration, it will occur at the vortex shedding frequency and will cause cross-flow responses. So we got the vortex shedding frequency at around 1.123 Hz, which gives us a tuning factor of 0.11, which is still very low and will not cause any resonance at our wind speeds until the speeds are more than 10 times, which is very unlikely. There will be some fatigue loading, but it's very less, and damping again causes smoothing of the response. To summarize, we have seen all the different load cases that the wind turbine tower experiences, and we can conclude that the tower is safe from all these wind loads. And now these are the references, and thank you. Now we will take questions. And just to add, this is the tower that has been constructed, and it was finalized and has been constructed at the site.
Questions? What is the meaning of the friction velocity?
Friction velocity. It is caused due to the surrounding terrain. And so basically there can be some, like the terrain can be smooth or rough. Depending on that, we generate a friction velocity. So we get that from basically the surface roughness length is included in the formula for that. So surface reference length is basically a reference to how smooth the surrounding surface is. So we chose to a rooftop mounted because of this. So we get the additional height from the structure itself. So the tower height will be small. So we get a steady wind flow at higher altitudes. So therefore, at that height, we get a less surface reference length, which decreases the friction velocity.
How can you determine the friction velocity that you measure?
No, it's there are some parameters. It's not exactly measured, but it it is actually very standard for, let's say, if you have a city region or a village region, there are some standards which are used. So it is empirically, it's not particularly measured as experiment.
What about the turbulence intensity? Did you evaluate that?
Yes.
Yes. But how was your the acquisition of your data? Because you said that the time between each acquisition point
Yeah,
was
so
quite
we
long.
got that from basically from the Taiwan spectrum, the critical Taiwan spectrum. That was modeled like basically for that we have the mean wind speed from our data. So this, actually that standard deviation itself is used for calculating the turbulence intensity.
Okay.
If I can step in, maybe. The turbulence intensity comes from the standard deviation, eta. And the eta itself is 2.5 times of the friction velocity, u star. And the friction velocity depends on the mean wind speed at that place and the z0, which is the surface roughness length. And that's a constant for a given kind of terrain. You are in the open ocean where you're installing an offshore wind turbine, then you'll have a very small roughness length. So usually turbulence intensities are really small, like 7% or so for offshore wind turbines, because the wind is flowing over a smooth surface. The moment you are in the city or in a vegetation area, you'll have more roughness and more turbulence. That's why offshore wind turbines are becoming more popular. The turbulence is less, so the quality of energy captured is higher.